This will be the last video of motors before we get into other subjects. So that's great. We worked our way down the timeline to the ECMs. This one here was also an ECM, and we talked about how this blower control board, the Carrier HK61E, was working on a PSC motor, and we didn't really hook it up to an ECM, but these ECMs now have the relays built into them, so it is the blower control board. So we skipped out on this part, and we're pretty much at the end of the timeline. I want you to stay tuned because we put a lot of tips in here, a lot of tricks too in the field. We have different perspectives that we want to show you how to test this motor, what this motor does on the terminals with live power. Stay tuned. Okay, we're over at the blower motor. This is an ECM motor. We're done talking about the PSC motors. We're not going to take it to the Cantex box today. We have a power supply here where we can give you a live power demonstration. We have our 230 volts line, and we have our secondary voltage, our control voltage, 24 volts. I'm going to go ahead and show you with my meter the voltage that we have. Between L1 and L2, I have a live 244 volts. Between R and C, I have 27.6 volts. And what we're going to do is we're going to take this voltage and we're going to go ahead and power up this ECM. Now before I do that, I want to go ahead and show you. I'm going to take the camera over there so you can see. If you look, this is already pre-wired. Now it's obviously not inside of an air handler, but you can see that we have a plug that's for our high voltage. And then we have our two connectors, the blue and the white, which are on terminal 2 and terminal 4. That's traditionally how you see it. And those are speed taps, and we're going to talk a lot about that. So I'm going to go ahead and take advantage of having all these connected to the motor already. And we're just going to touch them to our power supply, and we're going to get our motor to come on. And then we're going to discuss these speeds. We're going to discuss the 230 volts. And I'm also going to wire it to 120, which is not something that you're going to do in the field. But just to show you that this motor can run on 120 volts too. It's not running properly because this motor was wound up to run for 230 volts of electricity, not 120 volts of electricity. But still, even PSC motors, you can still create a path between common and run and still run it. You're going to obviously be outside of the amp draw that you're supposed to be, because if you typically drop your voltage, you raise your ampacity. So it's not something you would leave with a customer, but just if you wanted to take this home and plug it into the wall, mess around with it, I want to be able to show you that you can do that. This is a pretty neat motor because on the PSCs you had to integrate a capacitor and integrate a relay to get it to come on. Well, these motors, they have modules on the back side of them, and inside these modules there's already capacitors and there's already relays in there. As a matter of fact, this motor, when it gets the call for another speed, it will actually drop out one speed and pick up the next speed, so it will increase its speed if we apply 24 volts to another speed tap. I'm going to show you that too. And hopefully that helps illustrate when you have a call for a second stage, how this motor ramps up, and when you lose that call for a second stage, how it ramps down. The speed taps that are on here are where this blue and white wire are. I'm not going to change the speed taps with these. I'm actually going to have another demonstration where I show you with alligator clips very carefully on how we can get in here without all these plugs and see a little bit better the terminals. So what we're going to go ahead and do is we're going to go ahead and take our high voltage, separate those. We know we have black, we have yellow, there's obviously the green with the yellow stripe, that's our ground wire. And we're going to take these two and we're going to put these on our line voltage. And then we have brown, which is going to be common. All right, this is low voltage common. not high voltage common, okay? And then I have blue and white, which I can wire to 2 different speeds. Typically white is on a higher speed and blue is on a lower speed. That's how you'll typically find it in the field. And I'm going to show you real quick how easy this is. First, we're going to go ahead and wire up our line voltage. We're going to go ahead and connect one leg to one high voltage side of our motor. As you can see here, I'm just going to let this dangle, so it might be off screen. That's okay. And then I'm going to go ahead and take the other leg. Okay, so we have L1 and L2 now. And we're going to go ahead and wire it up to our other high voltage leg of our motor. Now we have 230 volts on this. We have to give it a common, a low voltage common. So I'm going to go ahead and wire low voltage common. We're going to go ahead and put that on the common side of our transformer. Okay, I'm going to go ahead and let this one hang down on this end over here carefully. We don't want that to touch anything. At least we don't want it to touch the high voltage. Let's see where it's going to fall. That's safe. And then we're going to take 24 volts, and I can hook this up to blue, which is on terminal 2. And just to kind of help demonstrate with the acoustics, I'm going to take my blue wire, which is on 2, and I'm going to go ahead and hook it up to 1. And I'm going to take my white wire, which is on terminal 4. I'm going to put it down on 5, because there's a big difference between terminal 1 and terminal 5 as far as speed taps go. And I want you to be able to hear those acoustics. So if I wire this to 1, this is low speed. And if I wired it to 5, that would be high speed. Everything in between is a version of medium. So medium low, medium, or medium high. So I'm going to go ahead and connect to our low speed terminal 1. I'm going to hold up the white wire because this is terminal 5. Okay, and I'm just going to keep this up. I'm going to go ahead and let this rest safely over here. And we'll go ahead and turn it on. Matter of fact, I'm going to go ahead and just remove power from my transformer so the motor will not run. Now that the breaker's on, we have live 230. I'm going to go ahead and connect 24 volts. As you can see, the motor's coming on, it's running. The only thing this is wired to is my blue wire, which is connected to terminal 1, which is low speed. I have my white wire, which is connected to terminal 5, which is high speed. And to show you here, I'm going to go ahead and connect 5 to my alligator clip and take the other end of my alligator clip. And I'm going to connect it over here to 24 volts. And you'll hear the motor pick up in speed. All right. And we are now running speed tap 5 only. It is ignoring the call for 1, but if we were to remove power on 5, the motor will reduce its speed to the last call, which is terminal 1. I'm going to show you with my timer what the off delay is once we remove power on terminal 1. And once we remove that, you're going to see a 90-second or a minute and 30 seconds, which will be 90 seconds. And that 90 seconds is going to be your off delay. Now, we talked a lot about off delays and why they're important. And it's the same thinking. And when we get to the smart board, we'll talk a little bit more about that. So anytime you're diagnosing these, you always want to see what is that off delay. Is my module okay? Does my module have a problem with it? And the only way to know that is to, put power on it and get it to run. And then once you remove power, you want to test it on that off cycle. So I'm going to go ahead and hit start. which I'm a couple seconds ahead of the game. As you can see, I removed power. And 90 seconds is a long time waiting on it. So if you're playing with low voltage wires and you're energizing and de-energizing these low voltage terminals for a fan call or whatnot, you're only going to increase that delay even longer. You know, so if I were to put power back on any one of those speed terminals and then remove it, it's an additional 90 seconds now. So when you're diagnosing these, you want to be patient. And as I always say, use a timer. Most cell phones have that. Little stopwatch there. And we're getting pretty close to a minute and 30 seconds or 90 seconds. And this motor is pretty consistent. I've tested it several times in our lab, so it should cycle off in about another 29 seconds here. These motors are a lot more efficient. They save money on energy consumption. Also keeping in mind with that off delay, they get more efficiency out of the equipment and transferring heat. All right, so it should be shutting off here pretty soon. And as you can see, it just kind of winds down, it's shutting off. And that's it. So I'm going to go ahead and hit stop. Reset, we'll probably wind up doing that again. All right, so I'm going to go ahead and turn the power off so I can safely remove my jumpers. And what I'm going to do is I'm going to give you a different perspective with the plug out. Remove all these terminals off of our power supply. And so as you see here, I'm unplugging the factory wires. And now we're going to look at the motor from a different perspective here. I'm going to go ahead and blow it up a little bit, get a little closer in there so you can see I have on the back side C, L, G, N. So there's 4 terminals. On the front side, I have 5 terminals. That's 1, 2, 3, 4, and 5. Now, 1 through 5 are your different speed taps. So 1 will be low speed, 5 will be high speed, and 3 will be medium speed. So that makes 2 with medium low and 4 medium high. And typically these come pre-wired for 2 and 4, which would be medium low and medium high. But you could put them wherever you need to. The reason why you're hooking 2 speeds up at a time is because if their heat strips are running, or if you have a second stage running, the motor needs to be pushing more airflow across either the heater element in conjunction with that evaporator coil if it's a heat pump. That way you don't cause any issues with the equipment malfunctioning because of the high head pressure or whatnot, or too much temperature in your supply air plumb. And so you have to have more airflow for that. So I'm going to give you this perspective, and we're going to wire these up with alligator clips. And with those alligator clips, we can, move these speeds around. And also I want to show you that if I used the L for one line and the N, instead of wiring it to the second line, I can wire that N to neutral, okay? And I will be able to take this 230 volt motor and run it on 120 volts. Now the amp draw will double. We're getting about 1.1 amps with it outside of the cabinet. And there's not much resistance on it, so it will increase the moment we put some static on it. I can't give you static in its application because it's just sitting on a free draw air handler stand, as you can see here. It's just sitting here. I got my power supply, I've got the motor, free draw stand, so I'm not able to give you the static pressure to get this motor to pick up in the proper CFMs. Now, if you see here, I got that green extension cord, okay? That's where I'm going to get my neutral from, and I'm going to go ahead and wire that up right now. Just give me a second. Because I'm in a situation to where it's in a lab and things have to remain safe, I'm going to pre-wire this and then turn the power on. So what we're going to do is we're going to first take out our extension cord, and we're going to plug into neutral. White wire and neutral. I'm going to see if I have a good neutral. We have 120. All right. So what we're going to do is we're actually going to take and we're going to wire. I'm going to go ahead and move my meter out of the way. We're going to wire the N terminal for neutral. I'm going to go ahead and wire that up. Just kind of leave that hanging out right there. Okay. Then I'm going to come over and I'm going to wire up L, which will be line. Okay, so there's the 120 now. And then we need to take common. Let me get my line back on there. Plug my line back in. We're going to take our common, our C, run it over to C on the box. Okay. And now the only thing we're missing is one of the speeds. And I'm just going to pick 5 and wire it to 5. Now I'm going to hold this in my hand. And what should happen, the moment I hit 24 volts, it's going to go ahead and turn on. All right, so as you can see there, I'm gonna go ahead and take the camera and show you. We have R and C. We only have one line, okay? You can see the neutral is just sitting on the extension cord. And if I get in here and show you with the terminals, I got 5 wired up, and then I have common, which is the green wire, black, which is going to L, and then I have white down here, which is going in. And I'm using this for my N for neutral. That's why they have it labeled N, is because it can be a second line voltage or it's just a path back. So this is just running on 115 volts right now. That's it. We have one leg of power. 24 volts, E-tap number 5, and then we're just using neutral here. And so I'm going to go ahead and do this again, but we're going to do it with the actual 230, because if I showed you my ampacity here, if I just clamped on this black wire, hopefully you can see that. You do it this way. You can see we're running 2.9 amps. And so that's going to be a lot less than that if we wind up running this 230 volts. I want to show you that difference there. All right, so we got the power turned off. All we need to do is take neutral, unhook it, and connect it to line. I'm already wired to 5. We now have 2 legs of power, L1 and L2. We're no longer hooked to neutral. see my white wire just dangling there. Okay, we have green for common. We have red 24 volts going up to terminal 5 for high speed. I have white and black, which is N and L. They're wired to L1 and L2. Okay, our line voltage. And I want to show you what that amp draw is now that we have 230 volts there. Go ahead and clamp it. And you see we're not getting 2.9, we're getting 1.8, 1.9 amps. That's a big difference here. All right, we're gonna go ahead and turn the power off. Okay, we're gonna show you one more perspective here. Just stay tuned. Okay, so I've got a closer image here of the terminals that we were talking about. 1, 2, 3, 4, and 5. And that's all going to be low voltage. Do not wire any high voltage to this. If you look over here on the back side, I have C, L, G, and N. So C is for common low voltage. So all these front terminals, 1 through 5, are going to be 24 volts input. The back terminal on the very top, C, that will be low voltage out back to the transformer. The L is line voltage, the G is for ground, and the N is for line voltage. Doesn't matter if you hook up L1 or L2 to L. It doesn't matter if you hook up L1 or L2 to N. It doesn't matter as long as we put 240 volts there. And so to wire this up, we're going to go ahead and take all of our alligator clips that I showed you in the other perspective, and we're just going to go ahead and wire by wire. We're going to go ahead and take L. We're going to go ahead and put, all right, so we actually have L connected. I'm going to go ahead and run my other leg of power up. And I'm using the same colors on the same terminals that I did earlier. So I have N, okay, and I have L. So there's my two legs of power. Now we're missing a common. So we're going to go ahead and take our green that we had wired to common earlier. We're going to head and run that back up here, get a good connection. Okay, make sure that's not going to pop off on us. All right, and now we have 1 through 5. So I'm going to go ahead and wire up terminal 1. Okay. Should see if you can see that okay. And I'm going to go ahead and do one more. Make sure this is going to reach. And when I'm ready, I'm just going to connect this to terminal 5 right here, and that'll rev that motor up. I think what I'll do is I'll go ahead and connect it to 5 now. See if I can leave a little bit of skin here, a little bit of metal. And then what I can do, that's not going to work very well. I was trying to connect it back up to here just to create a loop, but I don't know if I'll be able to do that very safely. So I'm just going to leave that connected there for right now. And we'll go ahead and put power on 5 here in a second. Right now, the motor's going to come on and run because it's already wired to run. Now that we have power, you'll hear the motor kick on. So now the motor is running. And we're running on speed tap 1, which is low speed. And the moment I take and put power on speed 5, you'll hear it kick up. And so there's still power on 1. Now I have power on 5. So the motor just revved up to its high speed. Now I'm going to go ahead and remove power on number 5, and you'll see that the motor will rev itself back down. And I'm going to show you that off the way. The moment we go ahead and remove power from 1, it's a 90-second off the way. "90 seconds is a long time when you're waiting on it, so you got to be patient when you're doing this." Like I said earlier, if I were to reapply voltage to any one of those terminals 1 through 5, this delay is going to start all over again the moment I release power. So if you need to be patient, and if you think your module has a bad relay where the module's keeping the motor energized because the contacts inside of it are stuck in a closed position, just like a relay could stick in a closed position, and a lot of times these things don't shut off, that's what's going on. Same thing, a lot of times you apply low voltage to them and they won't come on. Try different speeds. If you think your motor won't come on, you know, you have 1, 2, 3, 4, and 5. You know, try every one of those, put 24 volts on each one of those before you condemn the motor, because it may just be a bad module. And so there you go, it's very consistent. So if we had a motor that we thought was going bad, then what we would do is we would first put the 240 on it, make sure it has 240 volts. So we're going to check power between L and N. There should always be 230 volts there. And then I'm going to apply 24 volts to 1, 2, 3, 4, and 5 to see if I can't get that motor to engage. If I can get that motor to engage, then you do not have a bad motor. But if you have one of those terminals that does not engage that motor, then what you can do for your customer to get them back up and running is run the one speed that is working, or for that 24 volt contact, and order a new module for it. Now, sometimes motors come with the modules, or you may have to have one that's programmed or whatnot. But at the end of it, I want to show you here, how do you test the motor itself? And there's a way to test this in the field by removing the back of the motor. And so you can simply take your blower section out, just a couple screws, unplug it. You can see here we have a yellow sticker that says warning high voltage. Allow 5 minutes after power is disconnected before opening the motor. So power is still connected up here. So we're gonna go ahead and turn the power off, and it'll be 5 minutes before we do that. So we're gonna go ahead and show you another perspective. By the time we get set up here, 5 minutes would have passed. So stay tuned. All right, so now we're at another perspective here. As you can see here, we have the back side of the module. We've waited our 5 minutes, so we're gonna go ahead and show you how do I test if I think I have a bad motor. Now remember, there's a relay in here, so the only way I can test that if the motor has a open winding or if the windings are good, it's called the brake test. I would have to remove this module completely off of here. So I already got the screws loose. So I'm gonna pull these screws out, and I'm gonna show you, I'm gonna go ahead and unplug all the factory wires. And I don't have to remove the motor from the blower wheel, because I'm actually gonna use the blower wheel as my tool. And I'm just gonna simply just pull this module out, and you can see here that I have capacitors, and I have to be very careful not to go touching anything in here with my hands, because there may be energy that's still stored. I'm going to go ahead and unplug this from the motor. There's a plug here that's plugged into the module, and all I'm going to do is I'm going to simply just unplug this. There you have it. And now my module is separated. Okay, so you can take a paper clip, or you can take a, most of you have paper clips somewhere, right? Or you can just take a wire from, like a thermostat wire, 18 gauge wire. You can just strip it back. Whatever you want to do is you just want to make sure that you have a way to short out between the black and the red. I'm going to show you here. I just closed that circuit. That's all I've done. I'm going to let that dangle, and I'm going to try to spin the motor. And I know it's hard to see here, and I do have a light underneath it, but this motor does not want to spin. As you can see there, it's like spin the wheel. How long does it spin? It stops almost immediately. Now the moment I try to spin it and pull that out, as you can see here, it keeps spinning. And you can see it's still spinning right now. Still spinning. It's still spinning. And so that's not even a whole lot of momentum that I put on this thing, but this thing is spinning for, a good 15, 20 seconds here before it just stops on its own. And so if I were to see if I had a bad winding on this motor, I would simply just connect my paper clip in there like that to short out those two windings. I'm gonna try to spin it again. As you can see here, it stops. That's why we call it the brake test. And so if you have resistance on this motor, you can't have that resistance and have bad winding. So this would say, hey, in the event that my motor was not running and I went through terminals 1 through 5, and I tested 24 volts on each one of those, and I had a good common back to my transformer, and I had between L and N, I had 230 volts. If I had 230 and I had 24 volts input on 1, 2, 3, 4, or 5, and this motor would not come on, before I would condemn the motor, I would pull the module off the back of it, and I would just test to see if I had any type of resistance. And as you can see here, I mean, I got to really try to turn this thing. And so I'm getting a lot of resistance there, which says a lot about this motor. So this motor is good. And again, I'm going to go ahead and pull this back out and just show you it's still spinning. It's not stopping. The moment I put this in here, as you can still see it spinning here, it immediately stops. And so that's a good motor, so I would know that I have a bad module. Now, like I said earlier, if I can get one of these speed taps to run my motor, then I'm gonna probably apply 24 volts there at all times to make sure the motor does not turn off while I order the part. Sometimes these motors, once you get them going, they don't like it when they shut off when they have problems. So that's just another perspective to show you out in the field how to test out the motor from the module. Didn't require any voltage there. However, I did have to wait 5 minutes. As you can see here on the warning, it says allow 5 minutes after power is disconnected. They're talking about the 230 volts because there's stored energy on these capacitors. You see a couple capacitors in there, and you want to make sure that you're not becoming part of any circuit. As you know, capacitors store energy and they release energy the moment you become part of the circuit. So you want to make sure that energy is discharged. So they're making sure that you're remaining safe too as you're in the field testing these components out. Sometimes your manufacturers want to know, is it a bad module or is it a bad motor? And you have to know which one it is. If you are confused, you can easily tell if you have a motor that's bad or not. Okay, because if I had a bad motor, a bad winding, guess what? It's not going to stop. It's just going to continue to spin because I won't have resistance. That's called the brake test. Putting the motor module back together, it's simple. The plug only goes in one way. So you just line up the fittings, make sure it clips in, make sure it's not a loose connection. All right, you just simply put it back in. And as you can see, I didn't have to pull the motor out of the wheel to do that. Take your 1/4 inch machine screws, put them back in there. You always want to try to catch a few threads first before you put a drill on it. I like to hand tighten mine all the way so I know everything's good to go, so I don't cross thread anything. And then we'll just go ahead and tighten it back up. And that's it. So it doesn't take long to put it back together, test it, anything like that. So, and now that it's back together, I'll go ahead and spin it just to show you, it's perfectly fine. But that's the only way to be able to test those windings, because there is a relay in here that's in the normally open position. It is breaking a leg of power. So yeah, even though your motor has 230 volts on it, the motor actually doesn't have 230 volts on it, because if it did, it would run. It needs 24 volts to close the relay inside the back of the module, so it can run. That's why we don't run with relays or blower control boards anymore, because they're all built in here. And a lot of the times it's either maybe the capacitor's bad inside of here, maybe the board's got a short in it, possibility that the relay's not working, maybe it's stuck in the closed position, maybe it's stuck in the open position. And so you want to make sure that if it's under warranty that you're diagnosing it properly. And some of these manufacturers, they'll give you the entire component below or in module. Sometimes they want to know which components failed and they'll ship you that component. So you want to be accurate on your diagnostic. All right, so stay tuned. We're gonna take it to the smart board. Okay, we're at the smart board now. We're gonna go ahead and wire this thing up. That was pretty cool stuff that we went over. We went over the motor in different perspectives. Hope that helps you out. To show you that inside of an air handler would be very difficult, because to get in there with all the other wires that are busy in the air handler up, that just complicates things. And what we wanna do when we're showing these things is we wanna take things out of their normal application. Let's just talk about the subject. How do you talk about just the subject without getting your mind focused on everything else that's around it? We have to keep those other things in mind, but when we're diagnosing, we already know those other things don't matter, but we don't want to cloud our judgment. So we want to really home in on those components. What I'm holding up now is the back side of one of these motors. This is called a module. So when we talk about the ECMs, we have two components. We have the motor, and then we have the module. That whole combination together is an ECM, and it comes that way. We also have the factory wiring harness. We have the high voltage plug that also shares a low voltage path back to the transformer. It's a brown wire in this application here, and you want to make sure you never hook up high voltage to that. A lot of our trade, we see common. Oh, what is common? Is that high voltage? Is that common low voltage? This is very well expressed on a wiring diagram. If you can follow that wire back, it will trace back to the transformer. We're going to show you in case that diagram is not available to you on the smart board, so you understand how this thing is just wired up. Because what we want you to get out of this is there is no diagrams. I know how that thing works. I know how to diagnose it properly. I know how to test it. I know how to test my module out if my module's bad. I know how to test my motor out and see if my motor is good or bad, so I don't misdiagnose this. And some of those tips and tricks that we talked about, like the paper clip. You don't have to have a paper clip. You can take some 18/8 gauge thermostat wire, strip it back on 2 ends, fold it over to where you can actually get a little horseshoe. You can stick it in on the motor. I'm actually going to hold this up real quick just to show you that this is the motor we're talking about. If I pull that module off, I have a plug here, and as you can see here, I have the outer two. That's where I'm going to put the paper clip in, and I'm just going to stick this in here. And if I did that, you can't really tell with me holding this in my hand that it's not going to really spin. But as you can see here, I don't need a blower wheel to test this either. Right now, I have just shorted out, okay, those two windings, and I'm trying to turn my shaft, and it does not want to turn. It just does not want to turn. So I had to show you on a blower wheel because it was a lot easier. Plus, you may not want to remove your component if you're just diagnosing it, but it does not want to turn at all. I hope you can see that okay. But if I were to remove that paper clip out of there and then try to turn it, it's spinning. Okay, and so whether it's in or out, if you want to test it out of the box, if your customer wants to know, or if you're DIY, you want to say, hey, did I get another bad motor, out of the box, there's ways to test it, but you have to pull this off. And the reason why is because I'm actually breaking one of those windings across a relay, okay? And that relay is built into here. And so if I'm leaving everything plugged in, I'm not gonna be able to do it the same. I'm gonna have to take the module and disconnect it from that motor to test that out. Now, once we put power on this, 230 volts, it's like a capacitor. You put power on a capacitor, there's power on that capacitor that's stored. So you have to short those capacitors out so you don't, get any of that voltage that's stored. You don't want to hurt yourself. All these capacitors that are in here are also storing that energy too. There's a warning label on there for your safety. And make sure there's no power on it, no high voltage. The best way to do that, pull it out of the cabinet or unplug it. The other two wires that we haven't gone over yet, the blue and the white, we went over at the perspective of wiring it up. These two wires are for two different speeds, okay? The reason why we have two different speeds is in our trade, we have typically more than one stage of heat. And the event that we have to run at a higher CFM, we need to be able to pick up that speed. So when we get that additional call beyond just the call for a fan motor, like if I'm running a fan motor with the heat strips, okay, then I'm gonna have to bring my CFMs up. So now if I'm just wired to medium speed, it'll work on everything, right? But if I want to wire to a medium low speed and get a little bit more dehumidification out of the coil, a little bit more heating capacity out of the coil as I'm moving heat across it, or as I am dispersing the heat off that coil, then if I'm running heat strips in addition to that, I want to make sure that I pick up a little bit more CFMs so I don't sit there and have issues with limit switches, going bad because they're opening because the plenum temperature is too high. So they want you to pick up those speeds. So if you want it to run like a medium low, you can't run medium low in conjunction with a heating element. You have to run at a medium or medium high speed. And so that's why they come factory wired to medium low to get more cooling comfort out of it, and a medium high to run in addition with the call for fan with heat strips, because medium low is not enough CFMs. I'm going to go ahead and get right into this. I've labeled some of this, so I'm going to go ahead and just show you here that those speed taps 1 through 5. Here are the speeds and here are the CFMs. We have 1 is low speed. That's 350 CFMs per ton. And so if we had for example, if we had a 3 ton, we would multiply any one of these 3-digit numbers by 3. So we can do a couple here. We can say if I have medium speed times 3 equals 1200 CFMs, right? And so that's typically what we base everything off of anyways. And so they come wired up on medium low and medium high, right? And so as you can see here, if 400 CFMs per ton is the typical speed that you would normally operate on, if you're just dealing with a PSC motor and you're only running 1 speed and that's it, here they allow you to have those 2 speeds. So I'm getting more comfort with the ECM because I can run 2 different speeds. You're not running them both at the same time, but I can run this for my fan call anytime I get a Y call or a Y and an O call. But if I'm getting a Y and an O call or with a W call, then that's just not enough CFMs. I need to pick up those CFMs. And so it's pretty neat because I never lose 24 volts on this speed. I just gain 24 volts additionally on another speed, and it always will pick the higher speed. As I showed you in one of the perspectives, we wired to low, and then we wired to high. And the moment we had 24 volts there, we were running on low speed. We left that 24 volts there. When we put 24 volts on tap 5, it just went from low to high speed. And when we removed 24 volts from tap 5, it went immediately down to low speed. There was no delay. But when we removed power off of the low voltage terminals altogether, then there's a 90-second off delay. And we talked about that off delay extensively with the blower control boards and certain relays like sequencers, and any relay that pretty much has a built-in 24 volt power supply to allow the relay to stay energized anywhere between 50 to 90 seconds after the G call is gone. This module does the same thing. So you're still getting that, plus we have the 2 speeds. So a lot more comfort, a lot more efficiency. ECMs are the way to go. They also run at a lower ampacity, governing that you have the proper voltage on them. If your voltage is too low, your ampacity is going to be higher. If your voltage is right where it should be, then your ampacity will be at the design specs. Other things that are a factor on these ECMs and what causes these ECMs to go bad are high static pressure. So when we had it in our perspective in the lab, we had no static pressure on it because it was outside of a cabinet. And if you're testing this, your blower door is typically off. And if you're testing it, you're not going to be at the amp draws that you would normally be running at, or even be able to test static pressure because your panel is off, just like I couldn't with it sitting here on the table with just 230 volts on it. And so it's always good to test static pressure. We'll have other videos where we talk about static pressure and how that correlates with all types of key fundamental components like compressors, oil loss. Blower motors they're a key fundamental component, but they're not on the range of how much it costs. In that sense, you never want to lose a compressor. You can replace a motor a lot easier than you can a compressor. However, motors get replaced a lot in this field, and not because they just go bad. It's because something is killing them. Something is making those go bad. So if you're having problems with your ECM motor, they're a little bit more delicate than a PSC motor. And if you don't have good static pressure on them, if you're outside of that range, there's too much resistance on that motor, then your modules are going to fail. Not the motor, the modules are going to fail. Typically when your motor fails, it's a little bit more serious, but they do fail too. Caked up coils, that typically is going to kill the module. But I have seen plenty of motors go bad just because they've been running on too much resistance, and the windings just aren't built for that. So it's typically when you see that, the modules have been replaced a couple times and the motors eventually fail. Very important to know those key reasons why the motor is failing, so you don't just start replacing parts. Typically when you replace a part, you're not fixing the problem. When you replace the part, you're actually just treating the symptom. It's like anything else. You have a flat tire. Well, the tire didn't go bad. You ran over a nail or something, right? The nail caused a leak. You lost the air. The tire's flat. Car won't roll very well. And so if your motor has failed and you just replace the motor, if you don't find out what caused that motor to fail, then that motor will fail again. You can't blame it on voltage. You can't blame it on a lot of things that don't make sense. You have to start looking at other things. Is my coil clean? Okay, is it wired properly? Are my connections good? Do I have faulty connections? Do I have poor airflow across filters because they're not being changed often enough, and that's causing problems? Do I have improperly sized ductwork? There's a number of things. Somebody could have parked a Christmas tree you know, on this coming out of December, right on top of the main trunk line, and it could have collapsed it. You know, that'll cause it to fail. You can't go off the last time you're there. You have to be very observative. And sometimes those problems are very simple and they're just right underneath your nose. You just have to look for them. But there's a reason why those motors would fail. Getting right into wiring this up, I'm going to leave this here for a second before I erase it. Just like in the other videos, we had L1, L2 transformer, the low voltage terminal block. You can see here I've added the Y. That's because I have 2 speeds that I can actually now wire to. So I'm putting my W terminal there, obviously, or thermostat. This is the same motor diagram we used before. You're putting 2 legs of power there. All this stuff, there's no capacitor here because that's going to be built inside the module that I don't have expressed here in my diagram. You can clearly see that a leg of power is going to tie into these capacitors and provide that 3rd leg for my motor to have a start winding. So what we're going to do is we're going to just make it very interesting here, just to know that run and start are going to be on the same leg. Okay. When we wire this up, you want to wire 1 leg of power all the way through. When that leg of power is done, you want to go to the 2nd leg of power. This way we're observing both ends of the wires to make sure that we're not crossing paths of electricity, causing harm to yourself, most importantly. And then secondly, adding more work to your plate because you've created more damage to the equipment. Getting right into it, we're going to go ahead and wire this up. I'm going to go ahead and wire my transformer first because it's the closest high voltage component to L2 and L1. So we're going to go ahead and say I need L2 there. Where else do I need L2? Well, L2 has to make it to common, but it's going to first have to go to my module. So I'm just going to pick N just because N is a high voltage tap. I did show you that N could also be neutral. However, a 230 volt motor, you're not going to wire N to neutral because you're not going to get the proper ampacity, and those motor windings were not designed for that, and it will eventually fail. So don't take this out of a heat pump air handler, this 230 volt application, and use it in a gas furnace that's a 115 volt application. That's not going to be good. However, they put that there because traditionally, if that was on the motor, that module could work just as well for it. And in that theory, that's why they put the N there. I'm going to go ahead and take L2 as an input, and I'm going to wire to N. Okay. Now what's going to happen here is through the module, it's going to take N and it's going to wire it through that plug that we talked about, okay, to common. And what I'm talking about is on the back side of this motor, this plug here, okay, that's our 3 legs, our common, run, and start. All right, so we have L2 done. I'm going to go ahead and just label it L2, L2, and L2. We're going to go ahead and wire up L1. We're going to come off of L1, go ahead and go over to our transformer. Go ahead and label it L1. L1 has to make it to the motor, but first it's got to get through the module. So what I'm going to do is I'm going to come out of here. I'm going to come down to L for line. I'm going to go ahead and mark it L1. And then out of here, it's going to feed my run winding, and it's going to feed my start winding through that plug that we talked about. So I'm just going to put L1 and L1. So now you still know that these 2 windings are off of 1 leg. This winding is still off of another leg. There's just no capacitor for me to show you because all that's happening through the module now, okay? There's nothing else high voltage that we have to wire. We wired that portion. The G will go to ground, okay? I don't have ground up here in my diagram, but G will go to ground. We have common. This is not a high voltage common. This is a low voltage common. And then 1 through 5 are all 24 volt inputs. So this is going to be relayed from the thermostat. So we're going to go ahead and take 24 volts typically you would go through a fuse, maybe a transformer, a float switch, and then get over here to your low voltage terminal board. And then out of that, through your 18 gauge 8 thermostat wire, going over to your thermostat, that'll wire to the base plate, and that face plate will relay the power from here back through the face plate, back into the base plate, and correspond any terminal that it needs to relay 24 volts based on the programming of that interface on that thermostat. We're gonna go ahead and just switch some colors up. Common has to come back. So we're just going to put our common right back here on our transformer. While we're on common, before I change any colors up, I'm going to go ahead and say that common needs to come from the motor, which is on, typically it's the brown wire that's on the plug, okay? This is our low voltage common that I'm talking about. So this common here will come up and just give a path back to the transformer. So this common is a output. I'm going to put my little output arrow. Okay, so we have input, input. This is low voltage output. And then I just have to wire a couple of speed taps up. So basically, let's go ahead and just do a couple of these. Thermostat's going to put power out on Y. Thermostat's going to put power out on O. And then we're going to need a G call and a W call. The G call coming from the thermostat and the W call coming from the thermostat. Okay. G call's always going to come over here to typically your lower speed taps. It doesn't matter which two I wire up. Typically how you have it wired up, I'm going to wire it up that way, the way you would see from the factory, which is terminals 2 and 4. They're taking this G call and they're actually running this G call over here to terminal number 2. Okay? And so anytime this motor comes on, it's going to come on and run on medium low. Now you can raise that to another speed tap if you want to run at a higher speed. No problem. Just make sure the power's off, switch your speeds out, you're good to go. So 1 through 5 are all low voltage 24 volt inputs. Path is from the thermostat, okay? And they typically wire to terminal 2, which is medium low, which in between each one of these is 25 CFMs difference. All right, so 375 CFMs. I'm losing, if this was a 3-ton, I would be 75 CFMs less, so I would be at 1125 CFMs. So 1125 CFMs, it's not a lot of CFMs, but it's enough to make sure that we transfer enough heat, get a good, decent superheat, get a lot of comfort going for your home. But it's not enough speed to run medium-low with a heating element in conjunction with that. So that will cause some issues. So what they have done is they've actually taken the W, and if it's getting 24 volts, G's always there. They've taken that and they've wired that to your heat strips. And then also as a safety, if that relay ever sticks or if it's getting 24 volts, it comes back and it wires to terminal 4. Now I don't have a heating element up here, but if I did, simply I would say, here's my heating element, right? And I'm gonna run common and W up to it, and then out of here I would run back to 4. I'm gonna go ahead and erase that. And that's typically how that would be. In our diagram, what we're gonna do is we're gonna take our W and we're just gonna come out and we're gonna wire over to terminal 4. Now I can say that I want G to be terminal 3 and I want W to be 5. Okay, that's fine. I can run medium speed and high speed. But for the most comfort that you can get, the factory is already predetermined that, hey, why don't you run at 375 CFM per ton, and when you need a second stage of heat, we can go ahead and wire medium high up. Now, let's just say I had a Y1, Y2 situation, okay, and I had no electric heat. Now I can do the same thing. I can say, okay, Y1 low speed, I'm going to wire to terminal 2, and Y2 high speed, I'm going to wire here to terminal 4. Same thing, 2 stages. If I increase my BTUs, I need to increase my CFMs with those BTUs. All right, CFMs is your air handler, your BTUs is an output of the air handler, but it's as a result of what is it? Is it an output of the heat strips with, and then that's going to change with how much airflow is going across it. Is it an output off your evaporator coil because we're transferring heat from outside to inside? Those BTUs are always changing. So if our BTUs increase, we need to make sure that we can distribute that properly with the proper CFMs. And that's why these heat strips or Y2s will govern the next speed. And as long as this module is receiving 24 volts here, if it picks up 24 volt, call another one, you will hear that motor pick up. And you'll say, wow, I still have 24 volts between 2 and common, but I also have 24 volts between terminal 4 and common. Well, yeah, if you remove this last step here, it's just going to back its speed back down to medium low. Now, if I lose the G call completely, there's a 90-second countdown. And so I wanted to talk about that because I go over that extensively. And why is that important? For one, you can't get rid of it on a module, right? That's going to be there. It is designed to do that, to get as much comfort as possible. These manufacturers need to score in certain regions of the United States different SEER ratings, right? Whether you're SEER 1 or you're SEER 2. And so they're not going to compromise that because they're trying to deliver results that are regulated within this industry and not to be tampered with. And so they're very serious about that. So not a whole lot of wiggle room on trying to cancel some things out of here like you can on a PSC motor, where you can cut certain things that are shorted out and get rid of those time delays. Here you're going to have 90 seconds. Now, the problem with that 90 seconds that I see in our industry is the misdiagnostics that come out of it. Hey, my motor won't shut off. Okay, what do you think it is? Oh, the module's bad. Well, why do you say that? Because when I remove the call for G, it won't shut off. Well, the first question you should be asking yourself is, how long did I remove 24 volts? And did I have 24 volts removed on all of these? Maybe I was getting 24 volts here and I shut the call for G off, and maybe the other one was being back-fed voltage somehow. If you can say that there's no 24 volts between 1, 2, 3, 4, or 5, and you have sat there and you know that it's been a minute and a half, 5 minutes, 10 minutes, a day, whatever, and it just won't shut off, then you have a relay that is sticking, okay? You have a relay that is sticking. A lot of times you can just de-energize the air handler breaker. L1, L2 will lose power. It pretty much resets it. You can turn it back on. And a lot of times what you'll see is it'll come back on and that module will not be engaged and allow that motor to run. And then the moment you apply power, sometimes the problem goes away. Well, if you have already got to that point and you temporarily have got it working right, you still need to order the component that you need. If you're in the event to where you feel you have a bad motor and you're putting voltage on these and the motor's not turning and it's a warranty item and the manufacturer needs to know, is it the module, is it the motor? Simply detach the module from the motor and go ahead and do that brake test that we talked about and see if you have an open winding on the motor. If your winding is open, okay, then it's going to free spin. Now, if you think about it, you're going to try to free spin that thing, and if I don't care if you try to jump L and N out together, you know, which in your situation on the plug, that'll be the black wire, the yellow wire. You tie these things together, you are not going to get a brake test out of that. And the reason why is because one of those legs is going through a relay that you can't see because it's within the module, and so you're not closing. You're not short-circuiting that. You have got to take this module completely off and just simply take the motor. Like I showed you in one of the perspectives, I didn't have the motor out, but in this scenario, I'm holding it in my hand, and just go ahead and just short-circuit the last two wires on that plug, and you'll see it's very hard to turn the shaft on that motor, or it's very hard to turn the wheel. It's called a brake test. That's a very old technique. It's been out for a long time now. And at the end of it, you know, that basically just tells you, hey, my motor's good, I just have a bad module, because they may not give you what you need, and unless they are very sure that you're accurate on your diagnostic. Getting into that 90 seconds, if you want to kind of see what that looks like here. That 90 seconds, if we said 90 seconds was our off delay. All right, 90-second off delay. If we shut off 3 times an hour, that would mean like it ran for 10 minutes, it shut off for 10 minutes, it ran for 10 minutes, it shut off for 10 minutes, it ran for 10 minutes, it shut off for 10 minutes, it ran for 10, shut off for 10, ran for 10, shut off for 10, and it kept on doing that. And in 1 hour, okay, that was 3 on cycles and 3 off cycles, right? So with that being said, you would say, well, it shut off 3 times, and in that 3 times that it shut off, I would just multiply 90 seconds or 1.5 minutes times 3, were to come up to 4.5 minutes, an hour, that the blower ran past the time that the condenser shut off. Well, that coil that's underneath that blower or above it, whichever application you're in, positive flow or negative flow cabinet, your blower is exchanging heat still, okay, across that coil. So that coil is either going to be hot or that coil is going to be cold. And so we're still getting some heat transfer out of that. And that's what they're trying to achieve, because if they take this 4.5 minutes per hour, they multiply that over 24 hours, all right, and then we're going to multiply that again over just 30 days, okay? I'm going to show you what we come up with real quick. 4.5 minutes times 24 hours is 108 minutes. Okay, so 108 minutes. 4.5 minutes times 24 hours will be 108 minutes an hour. I'm going to go ahead and divide that by 60 minutes an hour. And I come up with 1.8 hours. I'm going to multiply that, 1.8 hours over 30 days. 1.8 hours over 30 days. Let's see what that comes up to. That is 54 hours per month. And if I wanted to see in a perfect world, if that was the case, 12 months out of the year, I'd multiply it by 12. 12 months equals 648 hours a year. So let's go ahead and just clean this up a little bit and talk about 648 hours. So that 90-second off delay in 1 year is 648 hours. 648 hours. That's a very, very, very long time that off delay is giving you. And out of that, that's 648 hours that if this is only running at, say, 1.9 amps of electricity, that's a lot cheaper to give you heat and cooling than the additional 12 to 18 amps that the condenser is going to be adding to that equation. And so that's the efficiency they're getting. So they're not going to let you tamper with that off delay, because these things are tested in a laboratory. These results are governed, very strict. You know, they want to make sure that their equipment is to the factory specifications at all time. And so there is no way of bypassing that. But that's very efficient. That's very good. And they want that 90 seconds. So, but a lot of the times our modules go bad because they don't shut off or they don't activate. And there's not a relay you can replace. And so a lot of times we have to go back down that timeline and put in a PSC motor, integrate either a relay or a blower control board, put a capacitor in to get that customer back up and running. And that's just what we have to do. We talk about that a lot. That's why we cover so much of these PSC motors. You can't get rid of them. They're always going to be there. And they're affordable truck stock item in comparison to an ECM motor. So that's pretty much all we need to cover on this. I hope this video helps you out. We're going to talk about a lot of other subjects now that we're done winding down with standard blower motors. We didn't talk about variable speed and the 16 pin. We'll release a separate video on that once we start getting more into zoning and stuff like that. Then we're going to start talking about static pressures and Y1s, Y2s, you know, your 3 heat, your 2 cool stages. We start getting into variable speed, it's better to start talking about dual stage compressors, stuff like that, so we can better understand these other speeds. So this is plenty of speeds to talk about and digest right now. That ECM just gave you 2 speeds that it can run that a PSE can't, right? If I try to run the PSE motor with 2 speeds, like low and medium, I'm gonna have a problem. It's not going to work out very well. I have to be able to drop 1 speed out to continue another speed. It can be done, but it's going to take a couple of relays to do that. And you know, that's really all there is to it. No light bulbs to wire up here. Could you integrate it? Yeah. Simple. When I get a 24-volt call, I can have that go to a relay, and building automation can be now implemented where I can have something else happen. You just have to put relays in. Long story short, that's pretty much it. Stay tuned to our next video. Like, subscribe, share this with others. That's your job. It's always your job. I hope this video helps the next person that hasn't seen it, and they're not going to know about it if you don't like, subscribe, and support the channel. Thank you.